Asteroids are among the most fascinating and enigmatic objects in our solar system. These remnants of planetary formation have captured the curiosity of astronomers, scientists, and space enthusiasts for centuries. To understand asteroids is to explore the building blocks of our solar system and to contemplate the role they may play in its future. Whether they are a potential resource for humanity or a threat to our survival, asteroids offer a unique glimpse into the universe's past while shaping discussions about our place in the cosmos. In the early days of astronomy, asteroids were not yet distinguished from planets. However, as telescopes improved and astronomers began observing the night sky with greater precision, the nature of these small, rocky bodies became clearer. Asteroids, unlike planets, are often irregular in shape, vary widely in size, and do not possess atmospheres. These small, rocky objects primarily orbit the Sun in a region known as the asteroid belt, located between Mars and Jupiter. This vast expanse, filled with millions of these celestial bodies, represents the remnants of a planet that never formed, torn apart by the gravitational pull of Jupiter during the early days of our solar system. Understanding asteroids begins with classifying them. Scientists have divided asteroids into three broad categories based on their composition: C-type, carbonaceous; S-type, silicaceous; and M-type, metallic. C-type asteroids are the most common, making up around 75% of known asteroids. These dark objects are composed primarily of carbon and water-bearing minerals, making them especially interesting in the search for clues about the origins of life. S-type asteroids, which account for about 17%, are made primarily of silicate and nickel iron. Finally, M-type asteroids, which are rarer, consist primarily of metallic elements, suggesting they may be fragments of larger bodies that experience significant internal differentiation during their formation. The asteroid belt itself is not the only region where asteroids are found. Near-Earth objects, NEOs, are asteroids that have orbits bringing them close to Earth's orbit. These objects are of particular interest and concern to scientists because of their potential to collide with Earth. Such impacts, though rare, have had significant consequences throughout history. The most famous of these is the impact event that is widely believed to have caused the extinction of the dinosaurs approximately 66 million years ago. This cataclysmic event, known as the Chicxulub impact, left a massive crater off the coast of Mexico and released an immense amount of energy, causing global wildfires, tsunamis, and a nuclear winter, effect that drastically altered Earth's climate. Today, scientists keep a close eye on NEOs, tracking their movements and calculating the likelihood of future impacts. Programs like NASA's Planetary Defense Coordination Office, PDCO, and initiatives by other space agencies around the world aim to detect, track, and study these asteroids. While the chances of a major impact in the near future are small, even a relatively small asteroid impact could cause significant damage, especially if it were to strike a densely populated area. One of the most ambitious and exciting developments in the study of asteroids has been the exploration of these objects through space missions. Several missions have already visited asteroids, returning valuable data and even samples to Earth. One of the most notable of these missions is NASA's OSIRIS-REx, which visited the asteroid Bennu and successfully collected a sample from its surface. Bennu, a carbon-rich asteroid, is of particular interest due to its potential to harbor organic molecules, offering insights into the early solar system and the building blocks of life. The Japanese space agency JAXA also made significant contributions to asteroid exploration with its Hayabusa missions. Hayabusa 2 visited the asteroid Ryugu, a carbonaceous asteroid, and returned samples to Earth in 2020. These missions provide unprecedented opportunities to study asteroids up close, analyze their composition, and better understand their potential as both resources and threats. Asteroid mining has been a topic of increasing interest, particularly in discussions about the future of space exploration and commercialization. Many asteroids, especially the metallic M-types, are rich in valuable metals such as iron, nickel, and even platinum. Some estimates suggest that a single asteroid could contain more metal than has been mined in all of human history. This has led to speculation about the possibility of mining asteroids for resources that could support space exploration, or even be brought back to Earth. While asteroid mining remains in the realm of speculation and planning, the potential rewards are enormous. Access to the raw materials found in asteroids could revolutionize industries, reduce the environmental impact of mining on Earth, and provide the resources needed for large-scale space exploration and colonization. Companies like Planetary Resources and Deep Space Industries have been at the forefront of these discussions, though significant technological and financial challenges remain before asteroid mining becomes a reality. As humanity looks to the stars for future opportunities, the potential role of asteroids in space colonization cannot be overlooked. One of the key challenges of establishing human settlements on other planets, such as Mars, is the need for a sustainable supply of resources. Asteroids could provide these resources, from water, in the form of ice, to metals needed for building structures and creating tools. By mining asteroids and utilizing their materials in space, future colonies could become more self-sufficient, reducing the need for costly supply missions from Earth. While the idea of living in space or on other planets may still seem like science fiction to many, the reality is that these discussions are happening now. NASA, SpaceX, and other space agencies and companies are actively working on plans for Mars missions, lunar bases, and more. In this context, asteroids represent both a challenge and an opportunity. On the one hand, they pose a potential threat to human civilization through impacts. On the other, they offer a wealth of resources that could enable humanity to establish a permanent presence in space. Beyond their practical implications, asteroids also hold a deep scientific and philosophical significance. Studying these objects offers us a window into the early history of our solar system. Asteroids are thought to be remnants from the time of planetary formation, pieces that never coalesced into full-fledged planets. As such, they preserve a record of the materials and conditions that existed billions of years ago, before Earth and the other planets took their current forms. By studying asteroids, we can learn about the processes that shaped our solar system and the forces that continue to influence it today. Moreover, asteroids also remind us of the fragility of life on Earth. The Chicxulub impact, which wiped out the dinosaurs, serves as a stark reminder of the potential dangers posed by space objects. While such catastrophic impacts are rare, they underscore the importance of understanding and tracking these objects. In a sense, asteroids are both a symbol of our cosmic origins and a reminder of our vulnerability in the face of the vast, unpredictable universe. As we continue to explore space, our relationship with asteroids will likely evolve. They may become key resources for future space missions, serve as destinations for exploration and research, and remain objects of fascination for scientists and the public alike. The study of asteroids is not just about understanding these small, rocky bodies. It is about understanding the broader processes that shape our universe and the future of humanity's place in it. In the years and decades to come, new missions to asteroids will undoubtedly uncover even more information about these enigmatic objects. As our technology improves and our understanding of the cosmos deepens, asteroids will continue to play a crucial role in our exploration of space. Whether as potential threats, valuable resources, or windows into the past, asteroids represent a fascinating and vital area of study, one that will likely shape the future of space exploration and our understanding of the universe. As we delve deeper into the vast expanse of asteroids, the future holds even greater potential for discoveries that will redefine our understanding of the cosmos. These small celestial bodies, once merely regarded as floating debris, are increasingly viewed as a key to unlocking numerous scientific mysteries. Their value extends beyond just their physical attributes. They are a record of the primordial ingredients that helped to form the planets, including Earth. Every asteroid we study offers us the chance to glimpse into the distant past, offering a narrative about how our solar system came to be and, more intriguingly, what lies ahead. One aspect that makes asteroids particularly intriguing is their role in delivering essential ingredients for life. It has long been theorized that asteroids and comets might have played a critical role in bringing water and organic compounds to Earth. These molecules, which are necessary for life, may have been deposited during the heavy bombardment phase of the early solar system when impacts were much more common. By studying asteroids that are rich in carbon, such as C-type asteroids, scientists hope to better understand whether the materials that seeded life on Earth came from outer space. Missions like OSIRIS-RX, which collected samples from Bennu, are already yielding valuable insights, as researchers analyze the chemical makeup of asteroid material. The idea that life's building blocks might have originated from space is not limited to Earth. Some scientists believe that asteroids could play a similar role on other planets or moons. For instance, the Jovian moon Europa, which is believed to have a subsurface ocean, might have been enriched with organic compounds through asteroid impacts. Likewise, Mars, which shows evidence of ancient water, may have received organic material through the bombardment of space objects. This possibility fuels the broader question of whether life might exist elsewhere in the solar system, especially in environments where asteroids may have delivered essential components. Asteroids may not only have contributed to the formation of life, but they may also pose a threat to its continuation. The impact of an asteroid large enough to hit Earth is a terrifying prospect, and while catastrophic events such as the one that caused the extinction of the dinosaurs are rare, smaller impacts happen more frequently than most people realize. The Chelyabinsk event in 2013, where a 20-meter asteroid exploded in the atmosphere over Russia, causing injuries and property damage, serves as a reminder that Earth is vulnerable to these space rocks. Although most near-Earth objects, NEOs, that could cause serious damage are being actively monitored, there remains an element of unpredictability, as some smaller asteroids may go undetected until they are too close to intervene. For this reason, planetary defense has become a major focus for space agencies across the world. NASA's DART mission, which aims to test our ability to deflect an asteroid by deliberately crashing a spacecraft into it, is a groundbreaking step toward developing methods to protect Earth from potential asteroid impacts. This mission, targeting the asteroid moonlet Didymos, represents a critical test of whether we can alter the trajectory of a potentially hazardous object. Although such technology is in its early stages, the results of DART could lay the groundwork for future strategies to deflect or destroy asteroids before they reach Earth's atmosphere. As scientists and engineers work to prevent potential asteroid impacts, the broader potential of these objects as a resource is also being explored. The concept of asteroid mining, once relegated to science fiction, is increasingly being taken seriously by companies and governments. As the resources on Earth become strained due to overpopulation and industrialization, the appeal of mining asteroids for metals and other materials grows. Beyond the wealth of precious metals such as platinum and gold, asteroids also contain elements like water ice, which could be critical for supporting long-term human presence in space. Water is essential not only for drinking but also for creating fuel through the process of electrolysis, which splits water into hydrogen and oxygen. Access to water-bearing asteroids could therefore be the key to sustaining missions to Mars or beyond, allowing spacecraft to refuel en route, reducing the need for carrying massive amounts of fuel from Earth. The possibilities that asteroid mining offers are vast, and while the technological hurdles are still significant, the potential rewards could spark a new space race, this time focused on exploiting the resources of space. One of the most important questions concerning asteroid mining is the environmental and ethical considerations that come with it. While mining asteroids might seem like a solution to Earth's dwindling resources, there are concerns about the sustainability and potential unintended consequences of such ventures. For example, introducing asteroid materials into Earth's economy could have significant impacts on global markets, especially for metals. There are also questions about the long-term effects of mining asteroids on space environments, and whether such practices could lead to unforeseen consequences, such as the creation of dangerous debris fields that could pose a threat to future space missions. Nevertheless, the excitement surrounding asteroid mining is palpable. Some visionary thinkers see it as a step toward space colonization, allowing humanity to expand beyond the confines of Earth and establish permanent settlements on the Moon, Mars, or even in orbiting space habitats. Such developments could shift the balance of human civilization, making space exploration more practical and less dependent on resources from Earth. Asteroids, in this context, would be essential not only for the materials they provide but also for the infrastructure they could support. The exploration of asteroids is not only about scientific discovery or resource acquisition, it also challenges us to rethink our place in the cosmos. Humanity has long been confined to the boundaries of Earth, looking outward toward the stars with wonder. Asteroids, small though they may be, represent the first real stepping stones to becoming a spacefaring species. As we learn more about these objects and how to interact with them, we move closer to a future in which humans may routinely live and work in space. This shift brings with it profound philosophical questions. If asteroids contain the building blocks of life and the resources needed for human expansion, what does that say about our relationship with the universe? Are we meant to be confined to our home planet, or are we destined to spread across the stars? The answers to these questions may not be clear yet, but the exploration of asteroids will undoubtedly play a central role in how we confront them. In many ways, asteroids represent both a challenge and an opportunity. They remind us of our vulnerability, as potential asteroid impacts could devastate life on Earth, but they also offer hope as a source of resources that could enable human expansion into space. As we continue to explore these objects, we are likely to discover new and unexpected insights, both about the formation of our solar system and about the future of humanity. Asteroids may be small, but their significance is enormous, influencing everything from planetary defense to the possibilities of human survival beyond Earth. Asteroids are much more than rocks floating through space. They are time capsules from the early solar system, reminders of the forces that shaped our world, and harbingers of what may come. By studying them, we unlock not only the history of our cosmic neighborhood but also the potential to shape the future of space exploration. The more we learn about asteroids, the more we realize that they are a crucial part of our ongoing quest to understand the universe and our place within it. Their mysteries, threats, and opportunities will continue to inspire curiosity and drive exploration for generations to come. As humanity looks toward the next frontier, asteroids stand as symbols of both the vast unknown and the enormous potential that lies in space. They are a challenge that we must confront with science, technology, and cooperation, but they also hold the key to a future where the resources of space are unlocked for the benefit of all. In studying asteroids, we are not just learning about our past but laying the foundation for a new era of human achievement. The journey to the asteroids is, in many ways, a journey to ourselves, as we seek to understand our origins, our future, and our place in the infinite expanse of the cosmos. As our understanding of asteroids deepens, so too does our awareness of the interconnectedness of celestial bodies in shaping not just the solar system, but life itself. Asteroids, though seemingly unremarkable in size compared to planets, hold secrets that touch on every aspect of cosmic evolution. From their formation, which tells us about the early solar system, to their ongoing influence on planetary bodies, asteroids remain at the center of some of the most critical scientific inquiries of our time. One of the most fascinating aspects of asteroids is their role in planetary evolution and development. Many planetary scientists believe that collisions between asteroids and young planets played a crucial role in shaping the surfaces of these planets. The constant bombardment by asteroids during the early history of the solar system, a period known as the Late Heavy Bombardment, left craters on planets and moons, including our own. These impacts were not merely destructive, they helped distribute material across the solar system, potentially seeding young planets with elements and minerals that contributed to their geologic and atmospheric evolution. This idea is closely linked to the hypothesis that asteroids and comets delivered water to the early Earth. The Earth, in its infancy, was a hot, molten world that likely lost any primordial water to space. However, the impacts of water-rich asteroids may have replenished the planet's water supply, setting the stage for the formation of oceans and, ultimately, the development of life. The isotopic composition of certain types of asteroids, particularly carbonaceous chondrites, is strikingly similar to the water found in Earth's oceans, lending credibility to the theory that water-bearing asteroids contributed significantly to Earth's hydrological history. Asteroids also serve as laboratories for studying planetary differentiation. Larger asteroids, particularly those that may have been on their way to becoming full-fledged planets before being disrupted, reveal clues about the internal processes that take place inside planets. Many asteroids have been found to contain layers, with heavier metallic elements like iron and nickel concentrated in their cores and lighter, silicate-rich materials making up their outer layers. This process of differentiation mirrors the geologic layering seen in planets, offering scientists a window into the formation processes that larger planetary bodies underwent during their early development. The study of asteroids is thus not only about understanding the objects themselves, but about piecing together the larger puzzle of planetary formation and evolution. By examining the composition, structure, and trajectories of asteroids, we gain insights into the forces that shape not only the solar system but also the conditions necessary for life to emerge on Earth. In this sense, asteroids serve as time capsules, preserving ancient materials and providing clues to the processes that took place billions of years ago. While asteroids are often associated with their role in shaping planetary surfaces through impacts, their significance in astrobiology, the study of life beyond Earth, has also become increasingly important. Asteroids may hold the key to understanding the distribution of organic molecules throughout the solar system. The discovery of amino acids and other organic compounds in meteorites, which are fragments of asteroids that have fallen to Earth, has ignited discussions about the possibility of life having been seeded from space. These molecules, which are the building blocks of proteins and other essential components of life, could have been delivered to Earth during the early bombardment period, contributing to the emergence of life. This notion raises exciting possibilities about the habitability of other worlds. If asteroids transported organic material to Earth, they might have done the same for other planets or moons in the solar system. Some asteroids, particularly those in the outer solar system, are rich in volatile compounds such as water ice, ammonia, and methane. These compounds are essential for the formation of complex organic molecules. Could asteroids have similarly seeded moons like Europa or Enceladus, where subsurface oceans might harbor conditions suitable for life? The idea that asteroids may have played a role in spreading organic material throughout the solar system has profound implications for our understanding of life's potential beyond Earth. Additionally, the search for extraterrestrial life has led scientists to examine the possibility that asteroid impacts on Mars or Venus could have created conditions conducive to the formation of life. While the surface of Venus is currently inhospitable due to its extreme temperatures and dense atmosphere, some researchers speculate that asteroid impacts may have temporarily altered its environment in the past, creating brief windows where liquid water could exist. Similarly, Mars, with its evidence of ancient rivers, lakes, and perhaps even oceans, may have been impacted by water-bearing asteroids, increasing the likelihood that the red planet once hosted life. As we expand our exploration of asteroids, the potential for astrobiological discoveries grows. Future missions to asteroids, particularly those that aim to return samples to Earth, will provide invaluable data on the types of organic molecules present in these objects and their potential role in the origins of life. The question of whether life is unique to Earth or widespread throughout the universe is one of the most profound inquiries of science, and asteroids may be the key to answering it. Asteroids are also at the forefront of new scientific and technological frontiers, especially in the context of space resource utilization. As humanity's ambitions in space grow, from establishing colonies on Mars to mining the Moon, asteroids are increasingly viewed as essential resources that could support long-term human space exploration. The water contained in some asteroids could be converted into fuel for spacecraft, while the metals found in M-type asteroids, such as nickel and iron, could be used for constructing habitats, tools, and infrastructure in space. This concept of using space resources, known as in situ resource utilization, ISRU, is a major focus of NASA and other space agencies. By harnessing the materials available in space, future missions could reduce the need for expensive and logistically complex resupply missions from Earth. Asteroids, given their rich deposits of metals and volatiles, are prime candidates for ISRU. One proposed idea is to create space-based manufacturing hubs where raw materials from asteroids could be processed into usable components for spacecraft or colonies. The technological challenges of asteroid mining are significant, but not insurmountable. Advanced robotics, artificial intelligence, and autonomous systems will likely play a key role in these ventures. mining asteroids in the microgravity environment of space presents unique engineering problems, but innovative solutions are already being explored. For example, some concepts involve using robotic swarms to break apart asteroids and process the materials in space, while others propose capturing entire small asteroids and transporting them closer to Earth or lunar orbit for easier access. In this future, asteroids could become central to the human presence in space, providing the raw materials needed for everything from spacecraft construction to life support systems. This shift in how we view and interact with asteroids is part of a broader transformation in humanity's relationship with space. No longer are we merely observers of these distant objects. We are now preparing to engage with them as integral parts of our expansion into the solar system. The economic implications of asteroid mining are profound. Some estimates suggest that the value of the metals and materials contained in a single large asteroid could surpass trillions of dollars. This has attracted the attention of private companies and investors, who see asteroid mining as a potentially lucrative new industry. Yet, as with any emerging industry, there are ethical and environmental considerations. The potential for asteroid mining raises questions about the long-term sustainability of space environments and the impact of human activity on celestial bodies. Could mining asteroids create debris fields or alter the trajectories of these objects in ways that could pose risks to other space missions or even Earth? As space mining technologies develop, it will be crucial to establish guidelines and best practices to ensure that the exploitation of space resources is done responsibly and with consideration for the long-term future of space exploration. In many ways, the story of asteroids mirrors the larger story of humanity's exploration of space. These objects, once viewed as mere cosmic debris, have become central to our understanding of the solar system and our aspirations for the future. They challenge us to confront fundamental questions about our place in the universe. How did life begin? Are we alone? What is our destiny as a species? Asteroids, in their complexity and mystery, offer clues to all of these questions, and the more we learn, the more we realize how integral they are to the broader cosmic narrative. As we continue to explore asteroids, both through telescopic observation and through direct missions, we will undoubtedly uncover more surprises. These small, rocky bodies may hold the key to understanding not just the past, but the future of our solar system, of life, and of humanity's expansion into space. The journey to the asteroids is just beginning, and as we stand on the cusp of a new era of discovery, these enigmatic objects will continue to inspire awe, curiosity, and ambition for generations to come. The possibilities are as limitless as the stars themselves, and the next chapter in our exploration of asteroids is likely to be even more extraordinary than we can imagine. As we continue to expand our knowledge of asteroids, the implications for the future of space exploration become even more profound. The prospect of mining asteroids, establishing sustainable colonies on other planets, and even using asteroids as waypoints or fuel depots for deep space missions highlights the critical role these celestial bodies may play in shaping humanity's destiny. However, before we reach the point of widespread asteroid utilization, there are several scientific, technological, and philosophical questions we must first grapple with. One such question revolves around the idea of asteroids as potential habitats for future space explorers. While the notion might seem far-fetched, it's not entirely out of the realm of possibility. Asteroids could serve as makeshift bases, especially if they contain resources like water ice that can be used for life support. Several scientists have proposed the idea of hollowing out asteroids to create space habitats, taking advantage of their natural shielding against cosmic radiation. This concept, while still theoretical, taps into the broader ambition of turning asteroids from passive objects into active components of human exploration and settlement in the cosmos. Such ideas represent a shift in how we think about space travel and colonization. Traditionally, discussions about space exploration have focused on planets and moons as potential sites for human activity. Mars, the Moon, and even Europa are seen as primary targets for colonization. However, asteroids offer a completely different and potentially more practical option. Their low gravity and abundance of resources could make them ideal for long-term missions that don't require the heavy infrastructure associated with planetary exploration. The hollowing out of asteroids, or the construction of habitats within them, is more than just a creative concept. In practice, asteroids have several natural advantages as potential bases of operation. For one, their orbits provide relatively easy access to both the inner and outer solar system. Asteroids in the asteroid belt, for example, could serve as fuel depots or rest stops for missions heading to Mars, Jupiter, or beyond. Their natural resources, including metals and volatiles, could be harvested for everything from construction materials to rocket fuel, reducing the need for Earth-based resupply missions. Furthermore, the idea of asteroid-based habitats speaks to humanity's adaptability and ingenuity. By using the materials already present in space, we can reduce the immense costs and logistical challenges of launching everything from Earth. This kind of in situ resource utilization, where we use local materials to build habitats, fuel spacecraft, and provide life support, is seen as a key to making long-term space exploration viable. Without it, missions to the outer solar system would be far more complex and expensive. The notion of colonizing asteroids also prompts us to rethink the way we imagine future human societies. In a world where asteroids become the stepping stones to the stars, we may witness the development of entirely new forms of life in space. Living on an asteroid or a series of asteroid habitats would necessitate new technologies, new ways of organizing communities, and even new forms of governance. Questions of ethics and ownership would arise. Who owns an asteroid? What are the rights of people living in asteroid colonies? These are not just hypothetical concerns. They are issues that must be addressed as we prepare for a future where humans become a multiplanetary, or even multi-asteroidal, species. The exploration of asteroids, then, is more than a scientific endeavor, it's a philosophical one. It forces us to confront the limits of our current frameworks for understanding property, sovereignty, and human rights in space. These questions are not just academic, they have real-world implications for the future of space exploration. As companies and governments invest in asteroid mining technologies, the need for clear ethical guidelines will become increasingly urgent. We must ensure that the pursuit of space resources does not lead to conflict or environmental degradation, either in space or on Earth. The principles of sustainability, equity, and fairness that guide environmental policy on Earth must also be extended to our activities in space. In addition to the ethical challenges posed by asteroid exploration, there are also significant technological hurdles to overcome. Mining asteroids, for example, is far from a simple task. Unlike mining on Earth, where gravity and infrastructure allow for efficient extraction of resources, mining in the microgravity environment of space requires entirely new technologies. Engineers are currently developing methods for anchoring equipment to asteroids, excavating material without causing the asteroid to break apart, and processing the extracted materials in space. These challenges, while daunting, are not insurmountable, and recent advancements in robotics, artificial intelligence, and spacecraft design are bringing us closer to the reality of asteroid mining. One of the most promising developments in this field is the use of autonomous spacecraft and robotic systems to perform the majority of the work in asteroid mining operations. These machines can be designed to operate in the extreme conditions of space, handling tasks like drilling, excavating, and processing materials without the need for human intervention. This not only reduces the risk to human life but also makes asteroid mining more cost-effective. By using robots to perform the labor-intensive tasks, we can focus human efforts on higher-level decision-making, exploration, and scientific research. The use of artificial intelligence in asteroid mining also has the potential to revolutionize how we explore space. AI systems can be used to analyze data from asteroids, identify the most valuable resources, and plan efficient mining operations. This level of automation will be crucial as we venture farther from Earth and begin to establish a more permanent presence in space. Whether it's mining asteroids, building habitats, or exploring distant moons, AI will likely play a central role in making these activities feasible. Of course, the technological advancements needed for asteroid mining and colonization are still in their early stages, and there is much work to be done before these ideas become a reality. But the progress made in recent years is encouraging. Missions like NASA's OSIRIS-RX and Japan's Hayabusa 2 have demonstrated the feasibility of landing on asteroids, collecting samples, and returning them to Earth. These missions have provided invaluable data about the composition and structure of asteroids, laying the groundwork for future exploration and resource extraction. In the coming decades, we can expect to see more ambitious missions that push the boundaries of what's possible in space exploration. Private companies like Planetary Resources and Deep Space Industries, along with national space agencies, are actively developing the technologies needed to mine asteroids and bring their resources back to Earth. These ventures, while still in the planning stages, have the potential to open up new frontiers of economic and scientific discovery. As we stand on the cusp of this new era in space exploration, it's important to remember that the pursuit of asteroid resources is not without its risks. The potential for environmental degradation, the ethical dilemmas surrounding space colonization, and the possibility of conflicts over space resources all loom large on the horizon. But with careful planning, international cooperation, and a commitment to sustainability, these challenges can be addressed. The exploration of asteroids is, in many ways, a reflection of humanity's enduring curiosity and drive to explore the unknown. These small, rocky bodies, once thought to be little more than space debris, are now recognized as critical to our understanding of the universe and our place in it. They hold the keys to our past, providing clues about the formation of the solar system and the origins of life on Earth. And they offer a vision of the future, where humans might live, work, and thrive among the stars. The story of asteroids is the story of human ambition. It's a story about pushing the boundaries of what we know, about reaching for the stars and daring to imagine a future where space is not just a destination for exploration, but a place where humanity can truly flourish. As we continue to study these fascinating objects, we are not just unlocking the secrets of the cosmos, we are also laying the groundwork for the next great chapter in the human story, one that will take us farther and deeper into space than ever before. As we venture deeper into the possibilities presented by asteroids, we can't help but reflect on the existential opportunities and challenges that lie ahead. Beyond their material value, asteroids compel us to confront broader questions about humanity's future. What does it mean for our species to expand beyond Earth? How will our relationship with space reshape our economies and ethical frameworks? And ultimately, what will our future look like when the resources, mysteries, and potential of the cosmos become part of our everyday lives? Asteroids are not merely space rocks. They are stepping stones to a deeper understanding of the solar system's evolution and the distant futures that may await us. The diverse characteristics of asteroids, from their compositions to their dynamic orbits, offer a wealth of information that scientists are only beginning to untangle. Each asteroid provides a snapshot of a time before the planets had formed, representing the building blocks that could tell us about the early solar system. These relics from the dawn of time contain critical clues to answering one of humanity's oldest questions: how did life itself begin? Many asteroids are composed of materials that are rich in carbon-based molecules, which are the fundamental building blocks of life. Some scientists speculate that life on Earth may have been jump-started by these asteroids or comets delivering organic compounds billions of years ago. Studying the organic chemistry of asteroids could help us understand whether the origins of life are a common event across the universe, or whether our existence is a rare anomaly. If these compounds can be found on asteroids throughout the solar system, it may indicate that life could be a frequent occurrence wherever conditions are right. The study of asteroids also holds implications for the search for life beyond our solar system. By understanding the conditions and materials necessary for life, scientists can refine their search for habitable exoplanets or moons in distant star systems. The study of asteroids, comets, and other celestial bodies thus serves as a bridge between planetary science and astrobiology, linking the physical processes of our solar system to the tantalizing possibility that life exists elsewhere in the universe. As we contemplate asteroids from a scientific perspective, we must also acknowledge the profound cultural and societal implications of exploring and utilizing them. The notion of asteroid mining, for instance, could revolutionize global economies. The sheer amount of metal, water, and other resources locked within these space rocks dwarfs the reserves available on Earth. Platinum, gold, nickel, and iron, all highly valuable on Earth, exist in far greater abundance on certain types of asteroids. A single metallic asteroid could hold more of these metals than has ever been mined on Earth, a fact that has sparked immense interest from private companies and governments alike. However, as tempting as it may be to exploit the riches of space, doing so without a plan for sustainability could have unintended consequences. The introduction of vast amounts of precious metals into Earth's economy, for instance, could destabilize markets and create enormous economic inequality. This raises ethical questions about how we manage the benefits of space resources, ensuring that they are distributed fairly and do not exacerbate existing global disparities. Moreover, the environmental implications of asteroid mining must be carefully considered. While mining on Earth has caused widespread ecological damage, space presents a new set of challenges. Removing resources from asteroids or altering their orbits could potentially change the dynamics of our solar system in ways we do not yet fully understand. The long-term consequences of such actions could include unforeseen gravitational disturbances or increased risks of asteroid collisions with Earth. In light of these risks, scientists, ethicists, and policymakers are beginning to emphasize the importance of planetary stewardship in space. This concept, which is akin to environmental conservation on Earth, suggests that humanity has a responsibility to ensure that its activities in space do not harm the broader cosmic environment. By approaching asteroid exploration with caution and respect for the delicate balance of the solar system, we can avoid repeating the environmental mistakes of the past. But beyond the pragmatic concerns of resource extraction and environmental preservation lies a deeper, philosophical question. What does it mean for humanity to become a space-faring civilization? For millennia, we have been earthbound, limited by the gravitational pull of our planet and the thin atmosphere that surrounds us. Space exploration represents our first steps beyond these constraints, into a vast and unknown frontier. Asteroids are not just objects to be studied or exploited. They are symbols of our species' unrelenting curiosity and our desire to transcend the boundaries of our current existence. In many ways, the exploration of asteroids is a metaphor for humanity's broader quest for knowledge. These distant, rocky bodies call to us from the far reaches of the solar system, promising answers to questions about our origins, our future, and our place in the universe. They remind us that we are part of something much larger than ourselves, a cosmic story that stretches back billions of years and will continue long after we are gone. By studying asteroids, we are not only learning about the solar system's past, we are also laying the groundwork for our future among the stars. This future, however, is far from certain. As we look to the stars, we must also consider the challenges that await us in space. The technical difficulties of exploring and exploiting asteroids are immense, and the political, ethical, and environmental issues are equally complex. But with careful planning, international collaboration, and a commitment to scientific integrity, humanity can rise to meet these challenges. We may still be in the early stages of asteroid exploration, but the possibilities are limitless. Asteroids could one day provide the raw materials for space-based industries, fueling the construction of space habitats, colonies, and spacecraft. They could serve as waypoints on our journey to Mars, the moons of Jupiter, or even beyond the solar system. And they could help us answer some of the most profound questions about life, the universe, and everything in between. The next steps in asteroid exploration will likely be defined by a combination of scientific discovery, commercial innovation, and international cooperation. Robotic spacecraft will continue to map and study these celestial bodies, while engineers and entrepreneurs develop the technologies needed to extract their resources. As we prepare for this new era of space exploration, it is worth considering the lessons we can learn from our experiences on Earth. The history of resource extraction on our home planet is filled with examples of exploitation, environmental degradation, and conflict. If we are to avoid repeating these mistakes in space, we must approach asteroid exploration with a sense of humility and a recognition of our responsibilities as stewards of the cosmos. Ultimately, the exploration of asteroids is about more than just science or economics. It is about the future of humanity. It represents our first steps toward becoming a multiplanetary species, expanding our presence beyond the confines of Earth and into the vastness of space. The challenges are great, but so too are the rewards. By studying and exploring asteroids, we are not only expanding our understanding of the universe, we are also expanding the horizons of what is possible for our species. The universe, in all its vastness, is filled with wonders waiting to be discovered, and asteroids are but one of the many mysteries that lie beyond our world. They are reminders of the untapped potential that exists in the cosmos, waiting for us to explore, understand, and embrace. The story of asteroids is not just a story of rocks hurtling through space. It is a story of human ambition, curiosity, and the unending quest for knowledge that drives us forward into the future. As we look up at the night sky and see the countless stars, planets, and asteroids scattered across the heavens, we are reminded that our journey is only just beginning. The exploration of asteroids is but one chapter in a much larger story, one that will take us farther than we ever imagined, to places we cannot yet conceive, and toward a future where humanity's destiny lies among the stars. The journey of asteroid exploration is poised to take us beyond the limits of our understanding, not just scientifically, but also philosophically, socially, and technologically. These celestial bodies, scattered throughout our solar system, hold the keys to unlocking new realms of possibility for humanity. They symbolize the inherent curiosity that drives our species, the relentless desire to explore, to push boundaries, and to understand the unknown. Yet, as we stand on the brink of an asteroid-driven future, we must also come to terms with the ethical, environmental, and existential implications of such endeavors. Asteroids, in their immense diversity, offer a natural laboratory to study the building blocks of our solar system. Each asteroid is unique, shaped by different conditions, histories, and compositions. Some are barren, metallic husks, rich in iron, nickel, and platinum, critical materials for future technological advancements. Others are rich in carbon-based molecules and water ice, hinting at the potential origins of life on Earth and other planets. By studying these variations, we gain insight into the early conditions of the solar system, the processes that form planets, and the elements necessary for life to emerge. For planetary scientists, this offers an extraordinary opportunity. The composition and isotopic ratios found in asteroid samples allow researchers to reconstruct the chemical environment of the early solar system. The findings from missions like NASA's OSIRIS-REx and Japan's Hayabusa 2 have begun to shed light on the similarities and differences between Earth and these space-bound objects. These missions, which have successfully returned samples of asteroid material to Earth, offer a glimpse into the future of asteroid exploration and the wealth of knowledge yet to be uncovered. Asteroids have an additional, albeit ominous, relevance to life on Earth, their potential for destruction. The threat posed by asteroid impacts is not merely a plot point in science fiction, but a scientifically recognized risk. While large, civilization-ending impacts are rare, smaller asteroid collisions occur more frequently than many might realize. In recent memory, the 2013 Chelyabinsk meteor that exploded over Russia injured over 1,000 people and damaged buildings in 6 cities. The prospect of an even larger asteroid colliding with Earth, one capable of causing mass extinctions, remains a pressing concern for planetary defense specialists. This ever-present danger has spurred international efforts to develop asteroid detection and deflection technologies. Early warning systems, based on telescopic surveys, are critical for identifying potentially hazardous asteroids long before they reach Earth. Missions like NASA's DART, Double Asteroid Redirection Test, which successfully impacted the asteroid moonlet Dimorphos in 2022, have demonstrated our growing ability to alter the trajectory of a space object. These advancements in planetary defense are essential to safeguarding life on Earth from future asteroid threats. But they also highlight the paradox of our relationship with asteroids. They are both a potential source of life's building blocks and a potential cause of its destruction. Beyond the immediate concerns of planetary defense and resource extraction, asteroids prompt us to think about our future in space on a more existential level. The notion of human expansion into space has long captured the imagination of thinkers, scientists, and dreamers alike. Asteroids, with their abundance of resources and strategic locations, are poised to play a crucial role in this expansion. They offer the potential for in situ resource utilization, where materials extracted from asteroids can be used to sustain life in space without relying on costly resupplies from Earth. This is an essential step in creating a self-sustaining human presence beyond our planet. One of the most tantalizing possibilities is the use of asteroids as way stations for deeper space exploration. As we look toward Mars, the moons of Jupiter and Saturn, and eventually interstellar travel, asteroids could provide both the resources and the fuel needed to make these journeys possible. By mining water ice from asteroids and converting it into hydrogen and oxygen, we can create rocket fuel for long-duration missions. This would allow spacecraft to refuel in space, reducing the need to launch massive amounts of fuel from Earth. In this scenario, asteroids become stepping stones for humanity's expansion throughout the solar system. Colonies and bases could be established on asteroids or in orbit around them, providing not only a way station for fuel but also a habitat for long-term missions. These asteroid colonies would require advances in technology, including artificial gravity systems, radiation shielding, and life support systems capable of sustaining human life for extended periods. But the rewards of such efforts are immense. They would bring us closer to the dream of becoming an interplanetary species. However, the expansion of human activity into space, especially in the form of asteroid mining and colonization, raises significant ethical and philosophical questions. As we begin to utilize the resources of space, how do we ensure that these activities are carried out responsibly? Space is a shared environment, and the actions of one country or corporation could have ripple effects throughout the solar system. The potential for environmental harm, including the disruption of asteroid orbits or the contamination of pristine celestial bodies, is real. We must develop robust international agreements and regulatory frameworks to govern space activities, ensuring that they are conducted sustainably and equitably. Moreover, the colonization of space, whether on asteroids, planets, or moons, forces us to reconsider concepts of ownership, governance, and human rights in a cosmic context. Who owns an asteroid? What are the rights of people who live and work in space? These questions touch on deeper issues about the nature of sovereignty, freedom, and justice in a future where humanity's presence extends far beyond Earth. As we contemplate these challenges, it's important to recognize that space exploration, and asteroid exploration in particular, is not just a technological endeavor, it is also a profoundly human one. It reflects our deepest desires to explore, to understand, and to find meaning in the cosmos. Asteroids, with their enigmatic pasts and vast potential, are a testament to the unknowns that still lie ahead of us. They remind us that, despite our technological advancements, we are still at the beginning of our journey into the stars. The study and exploration of asteroids will continue to push the boundaries of science and technology. As we develop new spacecraft, robotics, and AI systems to explore these distant objects, we will also be learning more about the broader universe and our place in it. The data gathered from asteroid missions will inform future generations of scientists and explorers, laying the groundwork for even more ambitious missions to come. In the grand scheme of things, asteroids are just one part of the vast tapestry of space exploration. But they represent a critical link between our past and our future, between the formation of the solar system and the next steps of human civilization. Their potential to reshape our understanding of the cosmos, to provide the resources needed for future exploration, and to pose existential risks to our planet makes them one of the most important objects of study in the coming century. As we gaze upward, wondering what lies beyond, asteroids remind us of both the opportunities and the challenges that await. They are symbols of humanity's unrelenting drive to explore and expand our horizons. They are keys to unlocking the mysteries of our solar system, and possibly the universe. But most importantly, they are stepping stones, guiding us forward into a future where the boundaries of space are not the limits of our ambition but the starting point of our greatest journey yet. With each new discovery, we move one step closer to a future where asteroids are not just distant objects in the night sky, but active participants in the story of human progress. The exploration of these space rocks, both scientific and industrial, will define much of humanity's relationship with space in the coming decades. And as we continue to unlock their secrets, we will come ever closer to answering the ultimate question: what does it mean to be a space-faring species? As humanity looks ahead, the exploration of asteroids emerges not just as a singular pursuit, but as a foundational aspect of our broader cosmic ambitions. These rocky remnants of the early solar system represent both an opportunity and a challenge, one that touches every facet of human knowledge, innovation, and survival. Asteroids, once feared for their potential to wipe out civilizations, now hold the promise of enabling us to thrive far beyond the confines of Earth. But to truly grasp the implications of asteroids in our future, we must explore several key dimensions: their role in expanding our scientific knowledge, the technologies needed to harness their resources, the ethical considerations of asteroid mining and colonization, and the profound philosophical implications of human life among the stars. At the heart of asteroid exploration lies a deeper understanding of our solar system's formation and evolution. As relics from the time before planets formed, asteroids are essentially time capsules, preserving the original materials and conditions of the early solar system. These rocky bodies offer scientists a way to peer back billions of years, to a period when the dust and gas surrounding the young sun were coalescing into planets, moons, and other celestial objects. By studying the composition of asteroids, scientists can reconstruct the chemical processes that led to the formation of the solar system, shedding light on the origins of Earth and, potentially, the emergence of life itself. One of the most exciting aspects of asteroid research is the possibility that these bodies hold answers to fundamental questions about life's beginnings. Many asteroids contain carbon-rich compounds and organic molecules, the building blocks of life. Some even possess water in the form of ice, which is critical for life as we know it. The discovery of these organic compounds on asteroids suggests that they may have played a role in seeding life on Earth. Some scientists believe that asteroids and comets delivered these key ingredients to our planet during its early history, kickstarting the processes that eventually led to the development of living organisms. This theory, known as panspermia, suggests that life's ingredients may be scattered throughout the cosmos, waiting to take root on planets with the right conditions. If this is the case, then asteroids could provide clues not just about the origins of life on Earth, but about the potential for life elsewhere in the universe. By studying asteroids, we could learn whether the processes that led to life on Earth are common throughout the cosmos, or whether life is a rare and unique phenomenon. The implications of such discoveries would be staggering, fundamentally reshaping our understanding of our place in the universe and the likelihood that we are not alone. In addition to their scientific value, asteroids hold tremendous potential as sources of resources for human civilization. Many asteroids are rich in metals such as iron, nickel, cobalt, and platinum, as well as rare earth elements that are critical for modern technologies. The value of these materials is immense, with some estimates suggesting that the metal resources contained in a single asteroid could be worth trillions of dollars. As the demands for these materials continue to grow on Earth, particularly in the context of renewable energy technologies and advanced electronics, asteroids represent a vast and untapped supply that could alleviate resource shortages and drive technological progress for centuries to come. Asteroid mining, therefore, is not just a distant dream, it is an emerging industry with the potential to reshape global economies. Companies and space agencies are already investing in the development of technologies that would allow for the extraction and utilization of resources from asteroids. The process would involve sending robotic spacecraft to survey and mine asteroids, extracting valuable materials and processing them either in space or on Earth. Water extracted from asteroids, for example, could be used to produce rocket fuel in space, enabling more ambitious missions to Mars, the outer planets, and beyond. The metals and minerals could be used to build space habitats, manufacturing facilities, and other infrastructure needed for a sustainable human presence in space. However, the prospect of asteroid mining raises significant ethical and environmental concerns. The commercialization of space, particularly the extraction of resources from celestial bodies, could lead to conflicts over ownership, regulation, and the fair distribution of benefits. Moreover, the environmental impact of asteroid mining must be carefully considered. While space may seem infinite, the ecosystems of our solar system are delicate, and altering the orbits or compositions of asteroids could have unforeseen consequences. The disruption of asteroids could potentially increase the risk of collisions with Earth or other planets, or it could interfere with the orbits of moons and other celestial bodies. Just as humanity has learned the hard lessons of environmental degradation on Earth, we must approach asteroid mining with a commitment to preserving the natural state of space, avoiding reckless exploitation that could lead to long-term damage. In this context, the concept of space stewardship is gaining traction. Much like environmental conservation on Earth, space stewardship advocates for the responsible and sustainable use of space resources, with an emphasis on minimizing harm to the cosmic environment. This approach would require the development of international regulations and agreements that ensure that asteroid mining is conducted in a way that benefits all of humanity, rather than a select few corporations or nations. It would also encourage transparency, cooperation, and accountability in space exploration activities, preventing the kind of environmental destruction that has plagued resource extraction industries on Earth. While the ethical and environmental dimensions of asteroid mining are critical, they are part of a broader philosophical question about humanity's future in space. What does it mean for humans to extend their presence beyond Earth, to live and work on asteroids, moons, and other planets? How will space colonization change our sense of identity and our values? These are questions that go beyond science and technology. They touch on the very nature of what it means to be human. The colonization of space, particularly of asteroids, would mark a profound shift in human history. For the first time, we would be living in environments radically different from Earth, with new challenges related to gravity, radiation, and resource scarcity. These challenges would require innovative solutions, such as the development of artificial gravity habitats, advanced life support systems, and new forms of agriculture suited to space environments. But they would also demand that we rethink many of our social and political structures. How would space colonies be governed? What rights and responsibilities would space colonists have? How would resources be shared? And how would conflicts be resolved in an environment where the stakes are literally cosmic? These questions are not merely theoretical. They will become increasingly relevant as space exploration continues to advance. The idea of asteroid colonies, once the stuff of science fiction, is now being seriously considered by space agencies and private companies alike. These colonies would likely begin as small research outposts or mining facilities, but they could eventually grow into thriving communities, with their own economies and governance systems. The people who live on asteroids or other celestial bodies would develop new ways of thinking about themselves and their relationship to Earth, as they become the pioneers of a new frontier. Asteroid exploration and colonization also raise profound existential questions. As we venture farther into space, we are confronted with the vastness of the universe and the relative insignificance of our planet in the grand scheme of things. Asteroids, as remnants of the solar system's formation, remind us of the impermanence of life on Earth and the fragility of our existence. The knowledge that an asteroid impact could wipe out civilization at any moment forces us to confront the precariousness of our position in the cosmos. At the same time, the potential of asteroids to sustain life and enable human expansion into space offers a sense of hope, a vision of a future where humanity is not confined to Earth, but spreads across the stars. As we explore asteroids, we are not just learning about rocks in space, we are learning about ourselves. We are learning about our origins, our potential, and the choices we must make as we move into the future. Asteroids are more than just scientific curiosities or resource-rich objects. They are symbols of the vast, untapped possibilities that await humanity in the cosmos. The exploration of asteroids will undoubtedly be one of the defining endeavors of the 21st century and beyond. It will require the collective efforts of scientists, engineers, policymakers, and philosophers to navigate the complex challenges and opportunities that these celestial bodies present. And as we venture further into the unknown, we must do so with a sense of responsibility, curiosity, and wonder, recognizing that the asteroids are not just out there, they are part of the same universe that we call home. The future of asteroid exploration is bright, but it is also uncertain. We stand at the threshold of a new era in human history, one in which the boundaries of space are no longer insurmountable, and the resources of the cosmos are within our reach. What we do with this opportunity will shape not only the future of space exploration but the future of humanity itself. Will we use the knowledge and resources of asteroids to build a sustainable, thriving presence in space? Or will we repeat the mistakes of the past, exploiting these celestial bodies without regard for the long-term consequences? The choice is ours, and the stakes could not be higher. As we continue our journey into the exploration of asteroids, we must consider the intersection of technology, ethics, and humanity's role as a cosmic species. In many ways, asteroids represent a microcosm of the challenges and opportunities that lie ahead as we push the boundaries of our existence beyond Earth. The question of how to approach these celestial bodies demands that we refine our tools and our understanding of the cosmos, while always being mindful of the broader implications for our planet, our civilization, and our collective future. One of the key technologies that will play a pivotal role in asteroid exploration is propulsion. Traditional chemical rockets have served us well for reaching nearby celestial bodies, but the distances and durations involved in deep space exploration require new innovations in propulsion systems. Ion propulsion, which uses electric fields to accelerate ions and produce thrust, has already been tested successfully in missions such as NASA's Dawn spacecraft. This technology allows for more efficient use of fuel and can enable longer-duration missions to asteroids that are farther from Earth. However, to truly unlock the potential of asteroid exploration, more advanced propulsion systems will be necessary. Concepts such as nuclear thermal propulsion, NTP, and nuclear electric propulsion, NEP, are being explored as ways to significantly increase the speed and efficiency of space travel. NTP, for example, involves using nuclear reactions to heat a propellant, which then expands and is expelled to produce thrust. NEP, on the other hand, uses a nuclear reactor to generate electricity, which powers an electric propulsion system like an ion thruster. Both of these technologies could reduce travel times to distant asteroids, making missions more feasible and cost-effective. Another area of technological development is robotics. Given the vast distances and inhospitable environments of space, robots will be the front line of asteroid exploration. Robotic spacecraft will be tasked with surveying asteroids, identifying valuable resources, and conducting initial mining operations. These robots will need to be highly autonomous, capable of making decisions and responding to unforeseen circumstances without direct human intervention, given the time delays in communication between Earth and distant asteroids. In addition to mining, robotics will play a crucial role in constructing habitats and infrastructure on asteroids. Future asteroid colonies will likely rely on 3D printing technologies to build structures from the materials found on site, reducing the need to transport large amounts of equipment and supplies from Earth. This approach, known as in situ resource utilization (ISRU), could revolutionize the way we approach space colonization, making it more sustainable and less dependent on Earth-based resources. Asteroid exploration forces us to confront deeper philosophical questions about our relationship with the cosmos. As we venture into space, we must ask ourselves, what is our purpose in exploring the universe? Is it simply to extract resources and expand our economic and political power, or is there a higher calling to be found in the pursuit of knowledge and the expansion of human consciousness? For some, the exploration of asteroids and other celestial bodies represents a continuation of humanity's long tradition of exploration and discovery. Just as our ancestors sailed across oceans in search of new lands and opportunities, so too will future generations venture into space, driven by the desire to push the boundaries of what is possible and to uncover the secrets of the universe. In this view, asteroid exploration is a natural extension of human curiosity and ingenuity, and it holds the promise of unlocking new realms of knowledge and understanding. For others, however, the prospect of asteroid mining and colonization raises concerns about the ethics of expanding human influence beyond Earth. Some argue that humanity's track record on Earth, marked by environmental destruction, resource depletion, and social inequality, suggests that we are not yet ready to responsibly manage the resources of space. They caution that without careful oversight and ethical considerations, asteroid mining could exacerbate existing inequalities, with powerful nations and corporations monopolizing the wealth of the cosmos at the expense of the global population. This tension between exploration and exploitation is not new. It has been a recurring theme throughout human history. However, the stakes are higher in space, where the consequences of our actions could reverberate for millennia. The decisions we make today about how to approach asteroid exploration will shape the future of space exploration for generations to come. In light of these ethical concerns, some propose that we adopt a more cautious approach to asteroid exploration, one that prioritizes scientific research and the preservation of space as a shared resource for all of humanity. This could involve placing certain asteroids off-limits to mining, much like the protection of natural parks and wildlife reserves on Earth. Alternatively, we could establish guidelines that ensure that the benefits of asteroid mining are shared equitably, with a portion of the profits being reinvested in global development initiatives or used to fund further space exploration. The philosophical implications of asteroid exploration extend beyond questions of ethics and economics. As we prepare to expand our presence into space, we must also grapple with the existential implications of living and working on asteroids. For the first time in human history, we will be living in environments that are fundamentally different from Earth, with new challenges related to gravity, radiation, and isolation. Living on asteroids or other celestial bodies will require profound adaptations, both physically and psychologically. The low gravity of asteroids, for example, could have significant effects on human health, particularly on our muscles and bones. Prolonged exposure to microgravity has been shown to cause muscle atrophy and bone density loss, and future asteroid colonists will need to develop new ways of maintaining their physical health in these environments. This could involve regular exercise, the use of artificial gravity habitats, or even genetic modifications to make humans better suited to life in space. Psychologically, the isolation and confinement of living on an asteroid could pose significant challenges. Astronauts on long-duration missions often experience feelings of loneliness, anxiety, and depression, and these effects could be even more pronounced for individuals living permanently on asteroids. Social structures and support systems will need to be carefully designed to ensure that asteroid colonists can maintain their mental health and well-being. This could involve the use of virtual reality technologies to simulate environments from Earth, regular communication with loved ones back home, or the creation of close-knit communities that foster social cohesion. The expansion of human life into space also raises questions about our relationship with Earth. As we establish colonies on asteroids and other celestial bodies, will we become less connected to our home planet, or will the experience of living in space deepen our appreciation for Earth and its unique ecosystems? Some argue that the exploration of space could lead to a renewed sense of environmental stewardship on Earth, as the fragility of life in space highlights the importance of protecting our planet's biosphere. Others worry that the ability to exploit extraterrestrial resources could lead to a devaluation of Earth's natural resources, with negative consequences for environmental conservation efforts. Ultimately, the exploration of asteroids forces us to confront the big questions about our future as a species. Are we destined to remain confined to Earth, or are we meant to spread out across the cosmos, becoming a multiplanetary species? What kind of society do we want to build in space, and how can we ensure that our actions today set the stage for a future that is equitable, sustainable, and just? These are not just technical questions. They are moral and philosophical challenges that require careful consideration and thoughtful action. As we look to the future, it is clear that asteroids will play a central role in humanity's cosmic journey. They offer the resources, knowledge, and opportunities needed to propel us into the next phase of space exploration. But they also present us with difficult choices about how to manage these opportunities responsibly, how to balance the demands of exploration with the need for ethical stewardship, and how to ensure that the benefits of asteroid exploration are shared by all of humanity. The next few decades will be critical in determining the course of asteroid exploration and the broader trajectory of human space exploration. As we venture further into the cosmos, the choices we make will define not only our technological capabilities but also our ethical and philosophical stance towards the universe we are beginning to explore. The questions and challenges will evolve, but they will always be rooted in the fundamental values that guide human progress and coexistence. The role of international cooperation in asteroid exploration cannot be overstated. Given the shared nature of space and the global impact of its potential benefits, it is essential for nations to collaborate, share knowledge, and develop joint strategies for the exploration and utilization of asteroids. International space missions, such as those coordinated by the International Space Station, ISS, and various space agencies, serve as models for how countries can work together towards common goals. These collaborations demonstrate that despite geopolitical differences, the pursuit of knowledge and the betterment of humanity can unite disparate groups in the face of a shared challenge. The formation of international partnerships for asteroid exploration could pave the way for more inclusive and cooperative approaches to space resources. By pooling resources, expertise, and technological capabilities, nations can address the technical, ethical, and logistical challenges of asteroid mining and colonization more effectively. This collaborative approach could also help to avoid conflicts over resource ownership and ensure that the benefits of space exploration are distributed equitably. One potential model for international cooperation is the establishment of a global space agency or consortium dedicated to the exploration and management of asteroids and other celestial bodies. Such an organization could oversee missions, regulate resource extraction, and ensure that environmental protections are in place. It could also serve as a platform for dialogue and negotiation, allowing countries to resolve disputes and share advancements in technology and research. The scientific community has a crucial role to play in shaping the future of asteroid exploration. Researchers and scientists will be at the forefront of developing new technologies, conducting experiments, and analyzing data from asteroid missions. Their work will drive the progress of asteroid exploration and provide the foundational knowledge needed to make informed decisions about resource utilization and space colonization. Furthermore, the scientific community must also engage with the public and policymakers to ensure that the broader implications of asteroid exploration are understood and considered. Public engagement and education are essential for building support for space exploration initiatives and fostering an informed dialogue about the ethical and philosophical issues involved. By making space exploration accessible and understandable, scientists can inspire the next generation of explorers and decision-makers, ensuring that humanity's journey into space is guided by a shared vision and a commitment to the greater good. The advancement of space technology will continue to push the boundaries of what is possible. Innovations in materials science, artificial intelligence, and data analytics will enable more sophisticated and efficient exploration of asteroids. For example, advanced materials could be developed to withstand the harsh conditions of space and the intense radiation found in asteroid environments. Artificial intelligence could play a key role in autonomous operations, allowing spacecraft and robots to perform complex tasks and make real-time decisions without human intervention. Data analytics will be crucial for processing and interpreting the vast amounts of information collected during asteroid missions, providing insights into the composition, structure, and potential value of these celestial bodies. In addition to technological advancements, the exploration of asteroids will require a strong ethical framework. As we venture into space, we must ensure that our activities do not repeat the mistakes of the past, where the pursuit of resources led to environmental degradation and social inequities. The principles of sustainability, fairness, and respect for the cosmic environment should guide all aspects of asteroid exploration and utilization. This ethical framework should be developed in consultation with a diverse range of stakeholders, including scientists, policymakers, ethicists, and the public, to ensure that it reflects a broad consensus and addresses the complexities of space exploration. As humanity embarks on this new chapter of exploration, we are also faced with the challenge of preserving the legacy of our endeavors for future generations. The decisions we make today will have long-lasting impacts on the future of space exploration and the development of human civilization. It is essential that we approach these decisions with foresight and responsibility, considering not only the immediate benefits, but also the long-term consequences for humanity and the cosmos. The exploration of asteroids represents a profound opportunity for growth and discovery. It challenges us to think beyond our current limitations, to innovate and adapt, and to reflect on our place in the universe. As we push the boundaries of space exploration, we are also expanding the horizons of human knowledge and experience. The pursuit of understanding and the quest for new frontiers will continue to drive our journey into space, shaping the future of humanity and our relationship with the cosmos. The exploration of asteroids is more than just a scientific and technological endeavor. It is a journey that touches on the deepest questions of human existence and our place in the universe. As we advance our capabilities and push the boundaries of space exploration, we must remain mindful of the ethical, philosophical, and practical implications of our actions. By embracing a spirit of cooperation, responsibility, and curiosity, we can unlock the potential of asteroids and chart a course for a future that is both sustainable and inspiring. The journey ahead is vast and filled with possibilities, and it is up to us to navigate it with wisdom and vision, ensuring that our legacy in the cosmos is one of discovery, stewardship, and hope. As we extend our exploration into the realm of asteroids, it's essential to address the various technological, ethical, and strategic elements that will shape humanity's interaction with these celestial bodies. This vast and multifaceted undertaking requires a detailed examination of the practical aspects of asteroid missions, the broader impacts on human society, and the future prospects of our spacefaring endeavors. Technological challenges and innovations. One of the foremost challenges in asteroid exploration is the development and deployment of advanced technologies that can handle the unique conditions of space and the specific demands of interacting with asteroids. The vast distances, low-gravity environments, and harsh conditions of space necessitate innovations across a range of technological domains. Spacecraft design and navigation. Designing spacecraft capable of reaching and operating on asteroids involves addressing several key factors. These include propulsion, navigation, and communication. Spacecraft must be equipped with advanced propulsion systems to travel the extensive distances involved. Innovations such as ion thrusters, which provide efficient and sustained thrust, are becoming increasingly important. However, for more distant and challenging missions, nuclear propulsion systems, such as nuclear thermal or nuclear electric propulsion, may offer the required speed and efficiency. Navigating to and landing on an asteroid presents additional complexities. The small size and irregular shape of asteroids make precise navigation essential. Spacecraft must be able to make adjustments to their trajectory in response to real-time data to ensure accurate landing or rendezvous. Technologies such as advanced gyroscopes, star trackers, and autonomous navigation systems will play a critical role in achieving these goals. Once on an asteroid, spacecraft must also be equipped to handle its low-gravity environment. Traditional landing techniques may not be effective, so alternative methods, such as using harpoons, drills, or even contact adhesive systems, are being explored. Ensuring that these systems can operate effectively in microgravity and resist the potential hazards of dust and debris is crucial. In situ resource utilization (ISRU). One of the most promising aspects of asteroid exploration is the potential for in situ resource utilization (ISRU). This concept involves using the materials found on asteroids to support human activities, reducing the need to transport resources from Earth. ISRU technologies could enable the extraction and processing of valuable minerals, water, and other resources directly on site. Water, for instance, is a critical resource for space missions. It can be split into hydrogen and oxygen for use as rocket fuel, providing a means of refueling spacecraft and supporting longer-duration missions. The extraction of metals and other materials could support construction activities, reducing the need for extensive supply chains from Earth. Advanced techniques for mining, processing, and utilizing these resources will be essential for the viability of asteroid mining and colonization. Robotics and artificial intelligence. Robotic systems will be at the forefront of asteroid exploration and mining. These systems must be capable of performing complex tasks in an environment that is remote and challenging. Advanced robotics and artificial intelligence (AI) will be crucial in managing these tasks. Robotic mining equipment will need to be highly adaptable, capable of handling various types of asteroid surfaces and compositions. AI-driven systems will be responsible for making real-time decisions, analyzing data, and performing maintenance tasks. The integration of AI will also enhance autonomous operations, allowing spacecraft and robotic systems to carry out tasks with minimal human intervention. Environmental impact. The environmental impact of asteroid mining and exploration is another significant concern. Although asteroids are distant and seemingly isolated, their exploitation could have unforeseen consequences. The potential disruption of asteroid ecosystems, even if minimal, must be considered. Additionally, the environmental impact of space missions, such as the generation of space debris, needs to be managed to avoid contributing to the growing problem of space junk. Establishing protocols for environmental protection and responsible exploration is vital to ensuring that space activities do not have adverse effects on the space environment. This includes developing technologies and practices that minimize space debris and carefully managing the impact of mining operations on asteroid surfaces. Human impact and psychological considerations. The prospect of human presence on asteroids brings with it psychological and social challenges. Living in the harsh and isolated conditions of space can have profound effects on mental health and social dynamics. Isolation and confinement. Astronauts and space travelers may experience feelings of isolation and confinement, which can impact their psychological well-being. The extended duration of missions and the confined space of habitats may exacerbate these effects. Addressing mental health concerns is crucial for maintaining the well-being of individuals involved in space missions. Developing strategies to support mental health, such as providing access to psychological support, designing spaces that promote social interaction, and ensuring regular communication with Earth, will be essential for the success of long-duration space missions. Cultural and social dynamics. As human presence on asteroids becomes a reality, the development of new cultural and social norms will be inevitable. The unique environment and experiences of living on an asteroid will shape the cultural identity of future spacefarers. The creation of supportive communities and social structures will be important for fostering a positive and cohesive environment. Future prospects and long-term goals. Looking ahead, the exploration and utilization of asteroids hold immense promise for the future of space exploration and human expansion into the cosmos. The advancements in technology, the development of ethical frameworks, and the successful management of psychological and social challenges will pave the way for the next era of space exploration. The long-term goals of asteroid exploration may include the establishment of permanent colonies, the development of space-based industries, and the advancement of scientific knowledge. As humanity ventures further into space, the lessons learned from asteroid exploration will inform our approach to other celestial bodies and contribute to the broader goal of becoming a multiplanetary species. The exploration of asteroids is a multifaceted endeavor that encompasses technological innovation, ethical considerations, and profound implications for humanity. The challenges and opportunities presented by asteroids are vast, and addressing them requires a collaborative and forward-thinking approach. By advancing our technological capabilities, developing ethical and regulatory frameworks, and addressing the psychological and social aspects of space missions, we can unlock the potential of asteroids and chart a course for a future that is both ambitious and responsible. The journey into space is a testament to human curiosity, ingenuity, and resilience, and the exploration of asteroids represents a crucial step in our quest to understand and navigate the cosmos. As we continue to push the boundaries of space exploration, the decisions we make today will shape the trajectory of our future in the universe. By embracing a spirit of exploration, cooperation, and responsibility, we can ensure that the legacy of asteroid exploration contributes to the advancement of knowledge, the expansion of human horizons, and the betterment of our collective existence. The path ahead is filled with challenges and possibilities, and it is up to us to navigate it with wisdom, vision, and a commitment to the greater good. The exploration and utilization of asteroids represent one of the most significant frontiers in our quest to understand and harness the cosmos. As we delve deeper into this subject, it becomes clear that the journey is not just about the technical achievements, but also about the broader implications for humanity and our place in the universe. To fully grasp the impact and potential of asteroid exploration, it is essential to explore various facets in greater detail. Asteroid missions, historical and current perspectives. To appreciate the evolution of asteroid exploration, it is useful to review both historical and current missions. The study of asteroids has progressed from early observations through telescopes to sophisticated space missions that have provided unprecedented data and insights. Early observations and theoretical foundations. The first asteroids were discovered in the early 19th century, with Ceres, Pallas, Juno, and Vesta being the initial members of this celestial category. These early discoveries sparked interest and theoretical speculation about the nature of these bodies and their potential significance. Observations from Earth, while limited by technology, provided crucial data on their orbits, sizes, and compositions. These early studies laid the groundwork for more detailed investigations. Pioneering space missions. The advancement of space technology enabled the launch of the first dedicated asteroid missions. NASA's Near-Shoemaker mission, launched in 1996, was a pioneering effort that studied the asteroid Eros in detail. Near-Shoemaker provided valuable data on the asteroid's surface composition, structure, and orbit. Its successful landing on Eros in 2001 marked a significant milestone in asteroid exploration. Following Near-Shoemaker, other missions have expanded our understanding of asteroids. The Japanese spacecraft Hayabusa, launched by JAXA, Japan Aerospace Exploration Agency, in 2003, targeted the asteroid Itokawa. Hayabusa's successful return of samples from Itokawa in 2010 provided unprecedented insights into the asteroid's composition and history. Recent advances in future missions. Recent advancements in technology have led to even more ambitious missions. NASA's OSIRIS-RX, launched in 2016, aimed to study and sample the asteroid Bennu. The mission, which successfully collected samples from Bennu and is expected to return them to Earth in the near future, represents a major leap in our capability to analyze and understand asteroid materials. Similarly, JAXA's Hayabusa 2 mission, launched in 2014, targeted the asteroid Ryugu. Hayabusa 2's successful collection of samples from Ryugu, along with its deployment of landers and rovers on the asteroid's surface, has provided valuable data that will enhance our understanding of asteroid composition and behavior. Technological innovations in spacecraft design. The success of these missions relies heavily on technological innovations in spacecraft design and engineering. Advancements in propulsion systems, power generation, communication technologies, and instruments have all played a critical role. Propulsion systems. Modern spacecraft utilize various propulsion systems to navigate the vast distances between Earth and asteroids. Traditional chemical rockets have been complemented by advanced systems such as ion thrusters, which offer higher efficiency for long-duration missions. Future missions may further benefit from emerging technologies like nuclear thermal propulsion, which promises to provide even greater thrust and efficiency. Power generation and management. Power generation and management are crucial for spacecraft operating far from the sun. Solar panels have been the primary source of power for most missions, but innovations in power storage and management are essential for long-term operations. Advances in battery technology and power distribution systems are enabling spacecraft to maintain operations during periods of limited sunlight. Communication technologies. Effective communication is vital for transmitting data between spacecraft and mission control on Earth. Innovations in communication technologies, such as high-gain antennas and advanced data compression algorithms, ensure that large volumes of data can be transmitted efficiently. The development of deep space communication networks will further enhance our ability to manage and coordinate future missions, instruments, and scientific tools. The success of asteroid missions also depends on the sophistication of scientific instruments on board spacecraft. Instruments for imaging, spectroscopy, and sample analysis provide detailed information about asteroid composition, structure, and surface processes. Advances in miniaturization and precision engineering have led to the development of highly sensitive and accurate instruments capable of conducting a wide range of scientific experiments. Asteroid mining and resource utilization. The potential for asteroid mining and resource utilization represents one of the most exciting prospects in space exploration. The idea of extracting valuable materials from asteroids has garnered significant interest from both governmental and private entities. Economic viability and market potential. The economic viability of asteroid mining depends on various factors, including the cost of space missions, the value of extracted materials, and the development of efficient processing technologies. While the potential value of asteroid resources is substantial, the initial investment required for mining operations is significant. Advances in technology and reductions in launch costs are essential for making asteroid mining economically feasible. Processing and transportation. Once extracted, asteroid materials must be processed and transported to Earth or used in space. The development of in-space processing facilities and transportation systems will be critical for the success of asteroid mining. Technologies for ore processing, material handling, and spacecraft refueling will play a key role in establishing a sustainable space-based resource industry. Environmental stewardship. The stewardship of space environments is a crucial ethical consideration. While asteroids themselves may be remote and seemingly insignificant, the impact of our activities on space environments must be carefully managed. The prevention of space debris, the minimization of contamination, and the preservation of cosmic heritage are all important aspects of responsible space exploration. Societal benefits and risks. The potential benefits of asteroid exploration, including scientific discoveries, technological advancements, and economic opportunities, must be weighed against the risks and uncertainties. The impact on global economies, the potential for new industries, and the societal changes resulting from space exploration are all factors that need to be considered. Public engagement and informed dialogue will be essential for addressing these issues and ensuring that space exploration serves the broader interests of humanity. The role of education and public engagement. Education and public engagement play a vital role in the advancement of space exploration. As space missions become more complex and ambitious, fostering public interest and understanding is essential for garnering support and inspiring future generations. Educational initiatives. Educational initiatives that promote STEM, science, technology, engineering, and mathematics fields are crucial for preparing the next generation of scientists, engineers, and explorers. Outreach programs, educational partnerships, and public awareness campaigns can help ignite curiosity and passion for space exploration among young people. Public engagement and communication. Effective communication of scientific discoveries and mission results is key to maintaining public interest and support. Engaging with the public through media, educational events, and interactive platforms can help demystify space exploration and highlight its significance. Transparent and accessible communication ensures that the benefits and challenges of asteroid exploration are understood and appreciated by a broad audience. The future of asteroid exploration. Looking to the future, the exploration of asteroids holds the promise of transformative discoveries and advancements. The continued development of technology, the establishment of international collaborations, and the resolution of ethical and regulatory issues will shape the trajectory of this exciting field. Human settlements and space colonization. As our capabilities evolve, the potential for establishing human settlements on asteroids and other celestial bodies becomes increasingly feasible. The development of habitats, life support systems, and sustainable practices will be essential for long-term space colonization. The experience gained from asteroid missions will provide valuable insights and expertise for future endeavors in space colonization. scientific discoveries, and cosmic insights. The study of asteroids offers a unique opportunity to gain insights into the early solar system, the formation of planetary bodies, and the potential for life beyond Earth. The data collected from asteroid missions will contribute to our understanding of cosmic history and the conditions necessary for life. Technological advancements and innovation. The technological innovations driven by asteroid exploration will have far-reaching applications beyond space missions. Advances in materials science, robotics, AI, and resource management will influence various industries and contribute to solving challenges on Earth. The pursuit of space exploration fosters technological progress and inspires innovation across multiple domains. The exploration of asteroids represents a monumental step in humanity's quest to understand and harness the cosmos. As we continue to push the boundaries of space exploration, we face both challenges and opportunities that will shape the future of our species. The technological advancements, ethical considerations, and societal impacts of asteroid exploration are interconnected and must be addressed with foresight and responsibility. The journey ahead is characterized by curiosity, innovation, and collaboration. By embracing these values, we can navigate the complexities of asteroid exploration and unlock the potential of these celestial bodies. The legacy of our efforts will be defined by our commitment to discovery, stewardship, and the betterment of humanity. As we explore the depths of space and the mysteries of asteroids, we pave the way for a future that is both inspiring and transformative, ensuring that our presence in the cosmos is marked by achievement, wisdom, and a shared vision for the future. As we continue to delve into the realm of asteroid exploration, it's crucial to understand the potential long-term impacts on various aspects of human endeavor. The interaction between humanity and asteroids is not just about scientific discovery or resource extraction. It involves a complex interplay of technological, ethical, and societal factors that will shape our future in profound ways. One of the significant aspects to explore is how asteroid exploration might influence our approach to planetary defense. With the increasing detection and tracking of near-Earth objects, NEOs, including asteroids, there is a growing emphasis on developing strategies to mitigate potential impacts. This involves not only identifying potentially hazardous asteroids, but also developing methods to prevent or deflect them if they pose a threat. The technology and strategies developed for planetary defense could have far-reaching implications, not just for protecting Earth, but also for advancing our capability to interact with and exploit celestial bodies. A critical area of focus is the advancement of impact mitigation technologies. For instance, methods such as kinetic impactors, which involve crashing a spacecraft into an asteroid to change its trajectory, or gravitational tractors, which use the gravitational pull of a spacecraft to gradually alter an asteroid's path, are under development. These technologies represent a blend of innovative engineering and deep space physics, offering practical solutions to an existential threat. The success of such methods will depend on continued research and testing, as well as international collaboration to develop and implement effective planetary defense strategies. Another important aspect of asteroid exploration is the potential for scientific breakthroughs. Asteroids are considered to be remnants from the early solar system, containing primitive material that can provide valuable information about the formation and evolution of our solar system. By studying asteroids, scientists hope to uncover clues about the conditions that existed in the early solar system and the processes that led to the formation of planets and other celestial bodies. This knowledge can deepen our understanding of fundamental questions about the origins of our solar system and the potential for life elsewhere in the universe. In addition to scientific research, asteroid exploration has the potential to revolutionize our approach to space travel and colonization. As technology advances, the feasibility of establishing human outposts, or even permanent settlements on asteroids becomes more realistic. These outposts could serve as stepping stones for further exploration and exploitation of space, facilitating missions to more distant locations, including Mars and beyond. The development of technologies for life support, habitat construction, and resource utilization in the low-gravity environment of an asteroid will be essential for the success of such endeavors. Moreover, the concept of asteroid mining could transform our economy and industry. The extraction of valuable metals and minerals from asteroids could alleviate resource scarcity on Earth and reduce the environmental impact of traditional mining practices. However, the economic viability of asteroid mining depends on numerous factors, including the cost of space missions, the efficiency of mining operations, and the market value of extracted materials. As technology advances and costs decrease, the prospect of asteroid mining becoming a significant industry becomes increasingly plausible. The societal impact of asteroid exploration and resource utilization cannot be overlooked. The potential for new industries, job creation, and technological advancements will have far-reaching implications for economies and societies worldwide. As space exploration becomes more integrated into our daily lives, public engagement and education will play a vital role in shaping perceptions and fostering support for space endeavors. Promoting STEM education and increasing public awareness of space exploration will help ensure that the benefits of these efforts are widely understood and appreciated. As we look to the future, the exploration of asteroids will continue to push the boundaries of human capability and imagination. The technological advancements, scientific discoveries, and societal impacts resulting from asteroid missions will shape the course of our spacefaring journey. The ongoing pursuit of knowledge and the quest for new frontiers will drive innovation and inspire future generations to explore and expand our presence in the cosmos. In essence, asteroid exploration is not just about reaching distant objects in space. It represents a broader endeavor to understand our place in the universe and harness the potential of the cosmos for the benefit of humanity. As we continue to explore and exploit the opportunities presented by asteroids, it is essential to approach these endeavors with a sense of responsibility and foresight. By balancing scientific curiosity, technological innovation, and ethical considerations, we can ensure that our journey into space is marked by achievement, sustainability, and a commitment to the greater good. The exploration of asteroids holds the promise of transformative discoveries and advancements, and it is up to us to navigate this frontier with wisdom, vision, and a shared sense of purpose. The quest to explore and understand asteroids is a reflection of humanity's enduring curiosity and drive to explore the unknown. As we forge ahead into this new era of space exploration, we must remain steadfast in our commitment to advancing knowledge, fostering innovation, and ensuring that our activities in space are conducted responsibly. The future of asteroid exploration is bright, filled with potential and promise, and it is our responsibility to embrace the opportunities it presents while addressing the challenges that lie ahead. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video if you found this video helpful and subscribe to the channel for more such amazing videos.